Hello, this is the third of a series of videos on multivariable calculus. So first we're going to talk about dot product, and then we'll discuss some properties of cross product. So as we discussed in the previous videos, we are going to study the geometry of three-dimensional space. So we talked about what points are, we talked about what vectors are, addition between two vectors, the scalar multiplication, and the dot product. So just to remind you, we had two formulas for the dot product. The first one is if you want to find the dot product of two vectors u and v, you multiply the corresponding components and then you add them up. So in this case, we multiply u1 and v1, and then we multiply u2 and v2, and we multiply u3 and v3, and then we add them up. The second method of evaluating the dot product is to find the magnitude of these two vectors, multiply them, and then multiply by the cosine of the angle between two vectors. So that's a formula that can be obtained by law of cosine. One thing that is really useful to know is that if the angle between two vectors is 90 degrees, if the two vectors are perpendicular, then cosine of theta is going to be 0. So cosine of pi over 2 is 0, which means u dot v is exactly equal to 0, because this term cosine is going to be 0. So in order to understand whether two vectors are perpendicular or not, what we need to do is to check whether the dot product is 0. So this is a really important property of the dot product. So let's do an example on this. We are given two vectors, 2c negative 3 and 1c2, and we are trying to figure out all the constants c that these two vectors are perpendicular. So what we need to do is to take the dot product of these two and see when the dot product is 0. So this gives us 2 times 1, which is 2. So when we find dot product of two vectors, we multiply the corresponding components. C times c, so that would be c squared, and then negative 3 times negative 2, which is negative 6. And this gives us c squared equals 4, which gives us two values of c. So c equals plus 2 and c equals minus 2 are the values that these two vectors are going to be perpendicular. Now that we understand dot product, let's look at one application of the dot product. One of the applications is the projection of one vector onto another vector. So let's imagine you have a vector A and you want to find the projection of that vector onto vector B. So we're going to see why we have this formula for projection. So in order to understand the projection vector, which is that green vector that you see, we have to understand its direction and its magnitude. Well, what is the magnitude of this projection? Well, magnitude is going to be, if you look at this right triangle here, because this is adjacent, it would be magnitude of A times cosine of theta. Now, if you recall, the formula for the dot product, which is what we just talked about, is product of the magnitudes times cosine of theta. Now, if we want to find magnitude of A times cosine of theta, we could simply divide by this, which gives us A dot B divided by magnitude of B. So this is how we can find the length of this projection. So this is the length of the projection. Now, what is projection of A onto B? What is the direction? Well, the direction is in the direction of B. It means we'll have to find the unit vector in that direction. So this is the unit vector in the direction of B. So we'll have to take this one and multiply by the length. So A dot B over magnitude of B. And when we multiply these, we get A dot B. And remember that A dot B is a scalar. The magnitude of B squared would be at the bottom times B. So this is the formula for the projection of one vector onto the other. So projection of A onto B is evaluated by A dot B divided by magnitude of B squared times the vector b. So projection is in fact a vector. So let's look at an example on this one. Find the projection of 2 minus I minus 2j onto I plus 2j plus k. So in this case, this one is A because it's projection of A, and the one at the bottom, that one is B. So what is the projection? What we need to do is first, we need to find dot product of these two. So A dot B, if we look at the formula that we have up here, so it's A dot B divided by magnitude of B squared, so magnitude of I plus 2j plus k squared, and then multiplied by B, multiplied by I plus 2j plus k. Okay, so let's do the computation and we get the final answer from there. The dot product would be you find the coefficients of I and multiply them. So the coefficient of y in the first one is 1 and the coefficient of I in the second one is also 1. So 1, and then we multiply -2, which is coefficient of j here, and 2, so that's -4, and then the other one is 0 times 1, so plus 0. At the bottom, magnitude of a vector is the square root of a squared plus b squared plus c squared, where a, b, c are the coordinates. So this would be 1 plus 4 plus 1, and then we multiply that by I plus 2j plus k. So to simplify, we get -3 over 6 times I plus 2j plus k, and -3 over 6 is -1/2, so we get -1/2 I, j, because it's -1/2 times 2, and then -1/2 k. So this is the projection of the first vector onto the second vector. Now, here is one application of the dot product. So I'm going to draw a diagram here. So in physics, we have learned what work is. So if you have an object under the influence of a force F and you move that, you have a displacement that takes this object and moves it to a different place. Let's say the displacement here is d. Then work done by this force is exactly force times d. That is when the displacement is in the same direction that the force is. So if the displacement and force are in the same direction, work is force times displacement. Now, what if it is not in the same direction? What happens if it is not in the same direction? Let's see what happens. So we have the displacement is from here to here, and I'm going to think about that as a vector. But let's say the force is a constant force, but in a different direction. So first we'll have to find the component of force in this direction. Well, because there is an angle here, in order to find a component in this direction, we'll have to use the right triangle here. So the force in the direction of D would be magnitude of F times cosine of theta. So work would be the product of these two, magnitude of F times cosine of theta times magnitude of d. And what is magnitude of F times magnitude of d times cosine of theta? That is exactly the dot product of F and d. So in order to in order to evaluate the work done by force F, we will find the dot product of force and displacement. Okay, so this is one important application of the dot product that we will be using that also later. The next thing we're going to do is the cross product of two vectors. So we have talked about operations between two vectors. We talked about the scalar multiplication and addition of two vectors. And then we talked about product of two vectors in one way, which is the dot product. The dot product gives us a scalar. So when you find the dot product of two vectors, you get a scalar, which means you get a number, not a vector. Now, we will discuss this cross product using a concept called the determinant. So a 2 by 2 determinant is defined by So you take A multiplied by D and then B multiplied by C, and then you subtract them. So multiply these two, and then you subtract them. How do we find 3 by 3 determinants? Well, there are a couple of different ways of evaluating 3 by 3 determinants. And if you are familiar with other methods, you could use those. But really, the only method that you need for this class is this method. So if you want to evaluate a 3 by 3 determinant, which is going to be really useful in this class, here's what we do. We are going to take the first entry of the first row, which is -1, and then we're going to eliminate the row of that entry and the column of that entry, and then multiply it by the remaining 2 by 2 determinants. So -2, 3, -3, and 2. Then we're going to move on to the next entry of this of the first row, which is 1. Eliminate the first row, eliminate the second column. So we have minus, and there's always a negative sign for the second entry. So -1 times, after removing the first row and the second column, we get a 2 by 2 determinant, 0, 3, -1, 2. So this is exactly these 4 entries right here. Then we move to the next entry here. So this is the entry. We're going to remove the first row again and the last column. So the signs alternate. The first one was plus -1, the next one was -1, and the last one is going to be plus 2. And then we are left with a 2 by 2 determinant. After removing the first row and the last column, we get 0, -2, -1, -3. Let's evaluate this, and that would be our final answer. So -1. Now here we have a 2 by 2 determinant, so we get -2 times 2 minus -3 times 3 minus parentheses 0 times 2 minus -1 times 3. And finally, we get plus 2 times 0 times -3 minus -1 times -2. And evaluating this, we get the final answer. So we get -4, minus -9, so that's plus 9, minus, that's 0. And here we get plus 4, plus 3, plus 2 times, that's 0, and that is minus 2. And this is pretty easy to evaluate. Okay, now that we understand how to evaluate determinants, we can understand how to evaluate the cross product of two vectors. So the cross product of two vectors u and v is a vector given by the 3 by 3 determinant obtained by placing I, j, k in the first row. So if u is u1, u2, u3, and v is v1, v2, v3, then what we do is this. We take a 3 by 3 determinant, we place I, j, and k in the first row, and then the second row would be u. So it would be u1, u2, u3, and the third row would be v1, v2, v3. Note that the second row must be the first vector, and the third row must be the second vector. So it is very important that we keep the order. If we swap the order, the answer would in fact be wrong. Let's look at one example. So let's say we want to evaluate the cross product of these two vectors. And then later we're going to talk about properties of cross product. So we want to find the cross product of these two vectors, I plus 2j and j minus k. So we're going to create a 3 by 3 determinant. The first row would be I, j, k. The second row would be the coordinates of the first vector 1, 2, and 0. And the third row would be coordinates of the second vector. So 0, 1, and -1. And then what we do is simply expand this determinant based on what we just learned. So we take this one. So I multiplied by the 2 by 2 determinant obtained by removing this row and this column, 2, 0, 1, -1. Now, we talked about how the second term would have to have a negative sign, and then we eliminate the first row and the second column. So minus j times 1, 0, 0, negative 1, and then plus k times 1, 2, 0, 1. And this is pretty easy to evaluate. I will evaluate that, but for later examples, I will just leave the calculation to you. This would be minus 1 minus 0 plus k times 1 minus 0. So this would be negative 2i plus j plus k. So that is the cross product of these two vectors. Now that we understand how to evaluate cross products, which is we understand the algebra, we want to understand the geometry. So what does it mean for us to find the cross product of two vectors? What are we actually evaluating? Well, first thing is if you take two vectors, let's say a vector u that moves to the right, so it's pointing to the right, and v that comes out of the screen. What is vector u cross v? There are two things that we need to know in order to understand the direction of u cross v. The first one is u cross v is perpendicular to both u and v. And by the way, cross product is going to be a vector, not a scalar. So u cross v would be a vector perpendicular to both u and v. So it would be either going up or going down. Now, which direction is it? The next one tells us what the direction is. So u cross v, u, v, and u cross v satisfy the right-hand rule. So starting from u, coming towards v, our thumb would point the direction of the downward direction. So this would be u cross v. And this one would be v cross u. So the one pointing up is v cross u, and the one pointing down is in fact u cross v. Now that we understand the direction, we want to understand the length of this vector, because for every vector we need to know its direction and we also need to know its magnitude. So what is the magnitude of this vector? The next statement number 4 tells us its magnitude. Magnitude of u cross v is going to be magnitude of u times magnitude of v times sine of the angle between u and v. Next property number 5, is that if you look at u cross v, that's exactly negative v cross u. So if u cross v points downwards, then v cross u would be the exact opposite upwards. If you take a vector with itself, then u cross u would be 0, because the angle between a vector and itself is 0. Therefore, u cross u would be 0. And then we have associativity. If you have a scalar, you can take it out of the cross product. And then we also have the distributive law. Okay. So one important property of cross product is we can use the cross product to find area. So if you have two vectors, let's call the two vectors u and v. We know that the angle between two of them is theta, some angle theta, and we know that magnitude of u cross v, based on what we just learned, is magnitude of u times magnitude of v times sine of the angle between them. Now, how do we interpret that geometrically? There's actually a very interesting way of interpreting that geometrically. So if you talk about this, if you take this height here h of the parallelogram, so I'm going to draw a parallelogram based on these two vectors u and v. This height, using this right triangle that we have here, is magnitude of v times sine of theta. So exactly this is exactly height. Now, if you take the height and multiply by the base, what do we get in a parallelogram? We get the area of the parallelogram. So the area of the parallelogram formed by two vectors is exactly magnitude of the cross product. So let's use that and do an example. Find the area of the triangle whose vertices are these 3 points. Okay, so in order to find the area of a triangle, we are going to use exactly what we just learned. So let's say A is 2, 3, -1, B is 1, 2, -1, and C is 0, 0, 1. We want to find the area of this triangle. Well, we know how to find area of a parallelogram. So what we do is we're going to create a parallelogram here. We are going to evaluate the area of the parallelogram, and then we are going to divide it by 2. So we look at this vector, we find the magnitude of the cross product. That would give us the area of the parallelogram, and then we divide that by 2. So area of ABC, triangle ABC, is equal to 1/2 area of parallelogram ABDC. In order to find the area of the parallelogram ABDC, we find the cross product of these 2. So AB is going to be, well, what is AB? We have to take the terminal and subtract the initial from that. So 1 minus 2, so that's -1. 2 minus 3, that's also -1. And then -1 minus -1, that's 0. And then we do AC. So C minus A. So 0 minus 2, 0 minus 3, and 1 minus -1. So that is 2. Now we're going to find AB cross AC. And that gives us the area after we take its magnitude. So IJK, AB is -1, -1, 0, and then AC is -2, -3, 2. Okay, so we're going to evaluate this. I times, so we have a 2 by 2 determinant, -1, 0, -3, 2, minus J times -1, 0, -2, 2, plus K times -1, -1, -2, -3. Okay, so let's evaluate this, and then we take the magnitude. So this would be -2 minus 0 minus J times -2 minus 0 again, plus K times 3 minus -2 times -1. So that is -2. So this is going to be minus 2i plus 2j and plus k. So area of the triangle ABC is going to be 1/2 magnitude of this vector, -2i plus 2j plus k. So that is 1/2 square root of 4 plus 4 plus 1. And that is 3/2. So that's the area of this triangle. Okay, so we're going to talk about one last thing and a couple of examples to understand how this works. The volume of the parallelepiped based on vectors u, v, and w is the absolute value of this dot product. So let's see how that works. So what is a parallelepiped? So if you look at a rectangular box, let me start from a rectangular box. So this is a rectangular box. It has 6 faces, and all of these 6 faces are rectangles, and the faces are going to be parallel to each other. So opposite faces are parallel to each other. So if you turn this one into something tilted, then you get something called a parallelepiped. So what is a parallelepiped? It's again a six-sided, it's an object with 6 faces, and opposite faces are parallel, and all of the faces are parallelograms. So if the vectors are, let's say this vector is u, let's say this vector is v, and this vector is w. So what do we want to do? We want to find the volume of this parallelepiped. So what is the volume of this parallelepiped? Well, the volume is going to be base times height. So base times height. Okay, so let's evaluate both of these, and then we are going to get the formula. So area of the base is a area of this parallelogram. So that one is the magnitude of V cross W, because that's the area of the base. Then we'll have to multiply it by the height. So let's look at what the height is. Well, if we look at V cross W, V cross W is in the direction of the height. So what is the height? Height is exactly this length right here. So let's say this angle here is theta. So in terms of theta, I can say that's just magnitude of U times cosine of theta. So what is magnitude cosine? Well, that's exactly the dot product. So that is U dotted with V cross W. Except because we want to find the volume, volume would have to be positive. So that's why I have to take the absolute value, because cosine could sometimes be negative. So that's the formula for the volume of the parallelepiped. Okay, so let's use that and do a couple of examples. The first example is to find the volume of the parallelepiped formed by these three vectors. So we need to find this quantity. So the volume would be absolute value of U dot V cross W. And it doesn't matter whether you do U dot V cross W or whether you do V dot U cross W. All of those are going to give you the same thing. So let's just start from V cross W. So this would be I, J, K. V is 0, 1, 0, and W is 2, 1, 3. Okay, so this would be I times determinant of 1, 0, 1, 3 minus J times determinant of 0, 0, 2, 3, and then plus K times 0, 1, 2, 1. So the first one is going to be 3I, the second one is going to be 0, and the last one is going to be negative 2K. So this is V cross W. And then we will have to evaluate U dot V cross W. So we'll have to take U, which is, we're given as 1, 2, 1. So I plus 2J plus K, that is U. And then we have to find the dot product of that with 3I minus 2K. So when you do the dot product, we'll have to multiply the coefficients of I, so that gives us 3. Coefficients of j, one of them is 0, so that just gives us 0, and then minus 2. So this would be 1. So this is the volume of the parallelepiped. Now, this is a positive number. If it were not, we would just simply take the absolute value. Okay, one last example, and then we are done. Show that these 4 points, A, B, and C, and D, lie on a plane. Okay, so what does it mean for these 4 points to lie on a plane? It means if you create so I'm going to call these 4 points A, B, C, D as they did. If you create a parallelepiped based on these 3 vectors A, B, AC, and AD, you would have to get a flat surface, because if they lie on a plane, there wouldn't be any height, which means the volume would be 0. So we need to show the volume, which is AB dot AC cross AD, is equal to 0. So that's what we're going to have to do. So let's evaluate AB. AB is, well, it's terminal minus initial, so minus 2. 2 minus 1, which is 1. Negative 1 minus negative 2, that is also 1. Then we evaluate AC. AC is C minus A. So 1. 1 minus 1, 0. Negative 3 minus 2, that's negative 1. And then AD, so D minus A. 0 minus 1, that's minus 1. 1 minus 1, 0. Negative 1 minus 2. Minus minus 2, that is 1. Now we do the cross product of these two. So AC cross AD is going to be I, J, K, AC is 1, 0, negative 1. AD is negative 1, 0, 1. Let's evaluate this and see what we get. So if we evaluate this, we get I times determinant of 0, negative 1, 0, 1 minus J times determinant of 1, negative 1, negative 1, 1, and then finally plus K times 1, 0, negative 1, 0. And if we evaluate this, we get 0i plus 0j plus 0k. Okay, so this is going to in fact be 0, which means the inner product is also, the dot product is also 0. So that means AB dot AC cross AD is also 0. And that's exactly, that exactly tells us that the 4 points lie on the same plane. Now, even if this were not 0, but the dot product were 0, they would still be on the same plane. So to close this, we're going to talk about, summarize what we did. So to check two vectors are perpendicular, we have to check that their dot product is 0. We talked about the formula of a projection. We talked about how to find cross product of two vectors, some properties of cross product, and finally the volume of the parallelepiped based on three vectors.